let's prove the following identity. So what this identity means is that if you sum n choose k with k varying from 0 all the way to n, you get 2 to the n. If you write this out, what we're saying is that n choose 0 plus n choose 1 plus all the way to n choose n minus 1 plus n choose n is equal to 2 to the n. So let's prove this, and it's a corollary of the binomial theorem. So what that means is that it follows directly from the binomial theorem. So consider the binomial theorem. So what was the binomial theorem? It said that x plus y to the power of n was going to be the sum from k equal to 0 to n of n choose k, so these were the binomial coefficients, x to the n minus k, y to the k. Okay, so this is what the binomial theorem says. And now, if we set x equal to 1 and y equal to 1, we obtain, so we get 1 plus 1 to the power n, which will be our 2 to the power n, right? And then on the right, we get summation of k equal to 0 to n, n choose k, and now 1 to the power of n minus k times 1 to the power of k, and simplifying, so simplifying, we get our result essentially. So on the left side we'll have 2 to the n, and on the right 1 to the power n minus k and 1 to the power k is just 1, so this would just be our summation of k equal to 0 to n of n choose k, which is exactly what we were wanting to prove. So you can prove this identity by just applying the binomial theorem and replacing values, right? Now let's show a different kind of proof that can also be quite enlightening many times, because it shows what this means in terms of counting. So let's see why this identity makes sense from a counting point of view. And this will be called the combinatorial proof. So let's suppose, so consider a set S with k distinct elements. So the cardinality of S is equal to k, right? So let's say in cardinality language, cardinality of S is equal to k. Okay. Now, if we look, so let's say we want to count the number of subsets of S, right? So let's put it here. So we want to count the number of subsets of S. So how many subsets does S have? So one way is to just count all of them by their sizes. So so how many subsets of size 0? So you have n elements and you choose 0 of them, so there's actually only one subsets of size 0, so which is the empty set, right? Because out of the n elements, there's only one way to choose none of them, which gives you the empty set. Then there are n choose 1 subsets of size 1. So n choose 1, if you compute it, is just going to give you n, so there's only n different subsets of size 1. And you can continue doing this, and you'll have that there are, in general, n choose k subsets of size k. And so if you sum all of them, so the amount of subsets then has to be equal to the sum of all of these, and choose 1 up to n choose n. So this is the amount of subsets of the set S, right? Now, there's a different way of counting it, which is the following. For each element, now we count it in a different way, so for each element of S, we have two choices. So we have two choices. Either we can include it in a subset, or we do not. So there are these two choices. Now, since there are n elements, then this gives us, so you have two choices for the first element, whether you include it or not into a subset, times two choices for the second element, and so on. So by the product rule, this gives us 2 to the n possible subsets. And so both of these count the same thing, and so they must be equal, which means that the sum of the n choose k equal to 0 to n, must be equal to 2 to the n. And so that's why that is the case. And so this is a good example of a combinatorial proof. And the idea is that we prove an identity by showing that both sides count the same object in two different ways.